So we're switching topics starting today to some extent. So we won't be talking about crystallographic root systems as the main object of study anymore. We have a big goal in mind for what's next. So our next big goal is to make an encyclopedia, basically, of all the finite Coxeter groups. So we're going to classify all the finite Coxeter groups. And as you can imagine, this is not exactly an easy task. We'll see if we can do it. But we're going to be using a lot of the theory of Coxeter groups that we've developed to actually understand exactly what are the finite Coxeter groups. Okay? So let me take the point of view now that if I have a Coxeter group, so Coxeter system, now let me call the generators S1 up to Sn. And let's say that I have a Coxeter matrix. So Mij is the order of Si is j. So given this, we have constructed the following. We have constructed a vector space which is n-dimensional. So V is an n-dimensional real vector space with basis given by things that are labeled alpha 1 up to alpha n, and we're going to think that they correspond to S1 up to Sn. Okay. Now the key thing that we're going to talk about today is the bilinear form. So we want to pay more attention to the bilinear form. That we put on this vector space. We know that to define a bilinear form, it's enough to define it on the basis. So I have to tell you what alpha j is, and we said that that was going to be minus cosine of pi over m I j. Okay. And so from the Coxeter group to the vector space with bilinear form. And this is the relationship that I want to talk about today. So before I talk about that, I want to give you guys a little bit of a review of bilinear forms if you've seen them already, and if not, then just tell you some basic facts about bilinear forms. So we have a vector space V, which is going to be n-dimensional, and a bilinear form is just something like this, where the input is two vectors in V, and now it comes, let's say, a real number in this case. Okay, and the idea is that it should be linear in each argument, right? Now, we can think of these more concretely if we choose a basis for B. So let's talk about what representing matrices are. So once you choose a basis for V, then you're going to have a matrix that represents the bilinear form. So I don't know, let's say that we have some basis E1 up to En. And then how am I going to represent things? Well, let's say that I want to know what the inner product of u and v is. Now, I write u in terms of my basis as u, I, e, I. I write v in terms of my basis as sum of v, I, e, I. Then so this is overall I. So what's u comma v? Well, basically it's this summation comma this summation. And now we use linearity, right? And by using linearity, what we're going to get is that we can take the summation out of the inner product and sum over, let's say that this sum ranges over I, this sum ranges over j. And so we're going to get basically the EI from here, comma, the EJ from here, and this EI has coefficient UI, and this EJ has coefficient VJ. Okay. So it looks like this. And if you think about this, we can write this very cleanly in matrix form, because this looks like multiplication of matrices if you just put this guy in the middle of these two. This is the multiplication of the matrices U1 up to UN, which is a row matrix. Then a square matrix, which looks like this, where I and j range from 1 to n. And then a column matrix V1 up to Vn. Okay. So if you don't see this right away, just think about what it means to multiply this times this times this, and you'll see that it gives you a number, and it's exactly this number that you get. So what's the point? Well, the point is that we chose a basis, right? And when you choose a basis, you can think of your abstract vector u really as a column vector, and v as a column vector, and it's exactly these vectors right here. Okay? And so really this is basically u. This is how we think of u in terms of those coordinates. This is how we think of v. And so the inner product of u and v is just going to be basically the vector for u, but let's say that these are column vectors, so we take the transpose just to get the right shape. Then this matrix, which maybe I'll call E, and then the column vector V. Okay? And so you see, if I want the inner product of u and v, all I have to say is what is u, what is v, and just multiply them by this matrix, which is encoding the bilinear form. Okay? This encodes the names of u and v, and this encodes the bilinear form. Okay? And so this matrix right here, E equals this thing. This is called the representing matrix with respect to this basis. Okay? And this proves again the point that if I want to define a bilinear form, all I have to do is tell you the product, what it is on the basis, and then by this recipe you know what it is on any u and v. Okay? So this is another way of thinking of a bilinear form. You can think of it as just some matrix in the middle of your u and your v. Okay? So this is a good thing to remember. But now, whenever you do this kind of thing, so we're still in the review of bilinear forms. Whenever you do this kind of thing, you not only want to know what happens when you choose one basis, but also what happens when you choose a different basis. Okay? Because if we were to choose a different basis, then we would get a different matrix. And then we would like to know how do you translate from this matrix to the other matrix. Okay? So let f1 up to fn be some other basis. Okay. And so this different basis is going to give me some different matrix, some different representing matrix, which is going to consist of the inner products of fi and fj. And so how do I go back and forth? Well, first of all, so let's do some basic linear algebra. The idea is, first of all, that if we make these bases make the columns of a matrix, then we can write that in terms of the old bases by just multiplying by some matrix here. M. So this is called the transition matrix from one basis to the other basis. Okay? So you just tell me how to write F1 in terms of the EIs and put that in the first column, in the first row, I'm sorry. How do you write F2 in terms of the EIs and put it in the second row? So this is the transition matrix. That tells me how to go from my old basis to my new basis. Okay? Some invertible matrix. Why is it invertible? Well, because this is a basis. Okay, so now let me tell you some basic facts about this. So first of all, U and V have coordinates U and V with respect to my first basis E1 up to En. That was by definition. Okay. So now I would like to know what are the coordinates with respect to the new basis. Of course, if I change bases, then my vectors are going to have different coordinates. And if you just think about this carefully for a second, you're going to find that all you have to do is multiply by M inverse on the left. And these will be the coordinates of U and V with respect to the new basis. Okay? And so the point is that I want to know what to write, what's the equivalent of this statement with respect to the new basis. And now I know that instead of U, I have to write M inverse of U, M inverse times U. Instead of V, I need to write M inverse times V because those are the new coordinate matrices for U and V. And now the question is, what does this become? Okay. How can I write the matrix of inner products Fi, Fj in terms of the one for Ei, Ej? Unfortunately, there's a nice way of doing that also, which is that if you want to know what this matrix looks like, well, basically, it's going to be this. It's going to be just the old matrix that you had multiplied on the left by M transpose and multiplied on the right by M. Okay. How do you prove something like this? You just compute. Okay. So you know what M is, you know what E is, you know what M is, and so you would just kind of multiply this out, see what the entry I comma j is, and you're going to find that it's exactly Fi of j. Okay? So it's a little computation that really you should do. So these are both good linear algebra exercises that you should do. So with respect to the new basis, how does this look? So with respect to the new basis, what equation do I get? Well, I get U comma V equals, instead of U, I have to write the new coordinates. So they're M inverse U transpose. Okay. Instead of E, I have to write the new representing matrix F, which looks like this. And in terms of V, I have to write the new coordinates, which are M inverse V. Okay. So this looks like a big mess, but if you just go ahead and compute this, well, first of all, you know that the transpose of a product is just reversing this thing. So you get U transpose. Now inverses and transposes commute with each other, so you might as well call this M transpose inverse. M transpose E M M inverse V. Okay, and everything cancels that you need to cancel. This cancels with this cancels with this, and you get U transpose EV. So that's good because you want to get the same number in this basis and in this basis. And so this is a good verification that what I'm telling you here, you know, if it's true, then I better get the same answer, and I did get the same answer. Okay. So this right here is the new representing matrix with respect to the new basis. New representing matrix. Okay. And these are the new coordinates for U and V. Okay. So do these exercises. This is good. Okay. So now, why do I mention this? Because here's a nice fact. Let's suppose that you have some symmetric bilinear form. So what does it mean to be symmetric? It means that the inner product of U and V is the same as the one for V and U for all U and V. Then what happens? What happens is that you have your representing matrix, which the entry ij is the inner product of ei and ej. Okay? But this is symmetric. This is a symmetric bilinear form, which means that the entry ij is going to be equal to the entry ji. Because the inner product of ei ej is the inner product of ej ei. So what you're going to get is that the representing matrix E is symmetric. Okay. So what are we going to do now? Well, the thing is, you know, as these things go, you have some bilinear form, right? And maybe you want to understand it in terms of a nice matrix. Okay. So maybe you pick some basis, and you got some matrix, and you think, man, I didn't really like the matrix that I got. Okay. So maybe I should have chosen a different basis. And if I manage to find a good matrix M so that this new representing matrix is much nicer, then I'm going to feel like I understand this form better because this matrix is simpler than this one. Okay? And so the question is, if I give you some matrix, E, can you get it into some nice form by multiplying it on the left by M transpose and on the right by M? Okay? Again, you have to think about what that means in terms of linear algebra. Multiplying on the left and on the right by matrices means doing row and column operations. And so really what I'm asking you is, if I give you some matrix, how do you get it into a nice form? By doing operations, row and column operations. Okay? And you guys know what you can do. If you start with any matrix, you can start doing row operations to make it upper triangular, right? Okay? But what if the matrix is symmetric? What if it's symmetric? Then you can do more, because if you do these row operations that make it upper triangular, and then you do the same column operations on the other side, then it's also going to be lower triangular, which means that it's going to be diagonal. Okay? So this should sound familiar to you from your linear algebra course. Any symmetric matrix can be diagonalized. Okay? So it can be diagonalized. Now, I should point out to you that the bilinear forms that we're studying are symmetric by definition, right? I guess I didn't explicitly write it there, but we have talked the whole time how these things are symmetric, and so I want to do this. I want to diagonalize them. Now, the way this is done is, like I said, we just apply some row operations on one side. I mean, again, you have to remind yourself why this is the way to write what I just told you. But the way you diagonalize the matrix is you do some row operations, you do the same column operations, and you get a diagonal answer. Okay? Where D is diagonal, And there's more, because these row and column operations that we do are what are called orthogonal matrices. And a matrix is orthogonal if its inverse equals its transpose. Okay. So this, again, this is not meant to be immediately obvious. This is a linear algebra fact that you should try to prove for yourself if you don't remember how to prove it. Okay. But what's the nice thing about this? You see, I have a symmetric bilinear form. I can diagonalize it in terms of an orthogonal matrix. Okay, M inverse is equal to M transpose, which means that I might as well put M transpose here. Okay, and so here was my old representing matrix, and by conjugating by M, I get a new representing matrix which is diagonal, and so that's much better, because we would much rather deal with diagonal matrices than to deal with some random matrices. Okay, so what this means is that if I think that this is the old representing matrix, this is going to be the new representing matrix, and it's a much better one. Okay, so that means that I can, if my bilinear form is symmetric, then I can choose a basis so that the representing matrix is diagonal. Okay. Which is great. Maybe we should think about the usual Euclidean product for a second. So let's think that now we're in Euclidean geometry. Now the bilinear form is just the usual inner product, the dot product. Okay, what's the representing matrix in that case? Well, first of all, what's the representing basis? Well, we like to think that we take the usual basis. An orthonormal basis is what we usually take. And why do we take an orthonormal basis? Well, the reason we do that is because if you look at the representing matrix, on the diagonal you're going to get EI comma EI, which is 1. Off the diagonal, you're going to get EI comma EJ, which is 0, because this thing is orthonormal. Okay? And the reason we choose something orthonormal is because then we get the identity here. And so the inner product is just U transpose V, and it's just the dot product. Okay? And so what I'm telling you is that we can do almost the same thing for an arbitrary symmetric bilinear form. We can almost choose this thing to be the identity. The only trouble is that it's not going to be quite the identity. It's going to just have things on the diagonal. Okay? But you can think of this as some kind of generalized dot product where you have to do UI times VJ, sorry, UI times VI times some constant that you're stuck with. It's not 1 in this case. Okay? So that's a very concrete way of thinking of bilinear forms. You can think of any bilinear form in that way as a dot product where instead, in front of the UI VI, you have some lambda I that you're stuck with. Okay, so that's a bit about bilinear forms. Now, the point of what I want to do next is basically try to tell apart what differentiates an arbitrary bilinear form from one that is Euclidean. Okay? And Euclidean bilinear forms have this nice property of being positive definite. Okay. So it's a big word, but all it means is that if you take the inner product of a vector with itself, you're going to get something positive. Okay? So that's all it means for a bilinear form to be positive definite. Okay? Now, of course, we know that Euclidean bilinear forms, The usual dot product is positive definite because this is just the square of the length of the vector in Euclidean land. And so that's going to be some positive number. Okay? But the nice thing about this is that actually this is an if and only if. Okay? So a symmetric bilinear form is positive definite if and only if it is the Euclidean inner product with respect to some basis. Okay. So like I said, one direction is trivial. We know that Euclidean inner products are positive definite. Okay. But actually the other side is pretty easy also, given what we've done, because basically we have an arbitrary bilinear form which is symmetric. And that means that we can find some basis so that the representing matrix looks like this. Looks like some diagonal matrix where we have zeros here, and we have numbers here. Okay. Now, what do we know about these numbers? Well, we haven't used the assumption yet that this is a positive definite thing. Okay. And positive definite means that when we take the inner product of the first basic vector with itself, we're going to get something positive. The second basis vector with itself is going to be something positive. All of these numbers are going to be positive. Okay. And so the representing matrix looks like this. Okay. Now, what do I want? I want this to be really the Euclidean inner product. Okay? In other words, what I want is that this representing matrix is not just kind of like the identity. I want it to be exactly the identity. Okay? So how can I get these things to be exactly ones? Well, I have some bases, right? And so I have some bases so that I have some orthogonal bases. Meaning that different basis vectors have inner product 0. Okay. And the only problem that I have is that E1 comma E1 is some positive number. E2 comma E2 is some positive number. And I would really like these to be ones, not some positive number. Okay. So how can I now change the basis again to make these exactly ones and not just d1 up to dn? Well, how do you take a vector of length 4 and make it into a vector of length 1? You just rescale it. So what do I need to rescale this vector by so that the inner product with itself is d1? Well, basically, this is like the square of the length. Okay. And so all I have to do is take F1 to be basically E1 over the square root of D1. Okay. And now I just scaled by the square root, which means that I'm going to get basically 1 over D1 times D1, which is 1. And I do the same for all of them. And I found that I have found not only an orthogonal basis, but an orthonormal basis. Orthonormal basis F1 up to Fn. And with respect to this basis, my new representing matrix looks like this. It's just 1s here and 0s here. It's the identity. And so my bilinear form is exactly the dot product with respect to that basis. Okay. So this is very good because I want to remind you of a statement that I've made several times, which is that finite Coxeter groups are the things that fit in Euclidean space. I always made this statement in a kind of a vague way, but we're getting to the point where we can actually make that statement precise. So what does it mean to fit in Euclidean space? Well, here's kind of an intrinsic way of thinking about that. You are Euclidean if your bilinear form is positive definite. Okay? If and only if. Okay? And so what do I mean exactly when I make that vague statement? That finite Coxeter groups are exactly the ones that fit in Euclidean space. What I mean is this. Okay. Theorem. A Coxeter group is finite if and only if its bilinear form is positive definite. Okay. So this theorem refers to this correspondence right here, okay, where you go from a Coxeter group to a bilinear form. Now, the Coxeter group is some algebraic object. You would like to know whether this algebraic object is finite. And this is kind of an amazing theorem that says, well, you don't have to go and count elements one by one. Okay? What you can do is just look at this bilinear form and see whether it has the property of being positive definite, where the bilinear form is defined in terms of the group only, not in terms of any particular geometric representation. Because of this claim that positive definite forms are exactly the ones that are Euclidean, this theorem is exactly what I have been referring to, that finite Coxeter groups are precisely the things that you can realize in Euclidean space. And this is the informal statement that I have made several times in this course, and now we're going to actually prove it. Okay. So we're going to spend the rest of this class and at least next class proving this theorem. Okay. And what I want to do for the rest of the class is prove this direction. Now, I should tell you, if you got a little bit lost with my discussion of positive definiteness and bilinear forms in general, well, this is a good point to start again, because basically the discussion that I just made was so that I could make this statement precise. Okay, and that's all I will need. And now to prove this theorem, I'm just going to use what positive definite means, which is this. Okay. Yeah.
I'm sorry. Is symmetry in here just to make this cleaner, or why is symmetry in there? Is that will we just have symmetry, or?
No, that's a good point. I didn't say it, but the dot product is symmetric. Right? And so that means that if you are a dot product, then you better be symmetric. Okay? And if you are symmetric, then I'm proving that you are a dot product. So that's just a tiny gap in my proof, because I didn't refer to the word symmetric, but that's a keyword. And what this claim says also is that if your bilinear form is not symmetric, then we're not saying anything about it.
So we're saying basically that all of our finite Coxeter groups will always be symmetric for bilinear forms because they're dot products.
But not only that, because by definition, the way that I define my bilinear form was in a symmetric way. I said that the inner product of alpha I and alpha j was, I defined it like this, so that this is equal to also alpha j and alpha I. I mean, the point is that the mij is equal to mji.
Right.
Okay? So that means that alpha I, alpha j is equal to alpha j, alpha I, which means that by definition, any bilinear form that we're going to encounter here is symmetric, which is why we can just, it's not a big deal to assume this, because in this class, bilinear forms are symmetric. Sometimes people need bilinear forms that are not symmetric, and then this doesn't apply to that situation. But we won't encounter non-symmetric bilinear forms. Okay. Now the thing about this proof is that, like I told you, people like to separate mathematics the way they like to separate church and state, and it just doesn't work that way. And so here we're actually going to need to use some other things. And so I'm going to assume a little bit of topology. But so if you haven't seen topology before, I'll tell you what the words are that I will be using, and I think this will make sense anyway. So let's assume that the form is positive definite. Okay. Now, we can think of our group as, like we said, we can think of our group elements as geometric things. Okay. We know that every group element, every generator we can think of as a reflection. And by composition, every group element we can think of as a linear transformation on our vector space B. Now, the thing about this is that, again, once you are willing to choose a basis, then invertible linear transformations are just invertible matrices. Okay? A linear transformation is just multiplying by a matrix. And it's invertible if and only if the matrix is invertible. Okay? So if I choose a basis, then I can think of this as n by n invertible matrices. Okay? And the n by n invertible matrices live inside the space R to the n squared. Right? These are real matrices, and so R to the n squared is, you can think of as the space of all matrices. Some of them are invertible. Okay? The thing about R to the n squared, the reason I want to do this is that here we have topology. We understand the topology of a real space, the usual topology. Okay? So let me make a claim. This is a very big group, okay? All the invertible matrices, there's a lot of them, infinitely many in a very big sense. And our Coxeter groups, well, we're trying to prove that this one is finite. But anyway, we don't think of our Coxeter groups as being so infinite. Maybe. The point is this. The point is that I want to make that more precise by saying that this thing which lives inside here is not as infinite in the sense that it is discrete. And what this means is that it has no accumulation points okay. And the way you should think about this is that here's this huge GLV, okay? W lives inside there. So discrete means that it looks like the way I'm drawing it. It wouldn't be discrete if you had limit points like this. You know, if you had like something like this, and you had a limit point, this would be called an accumulation point, and that's what I'm claiming we don't have in Coxeter groups. So proof. How am I going to prove this? Well, let's assume that we do have an accumulation point, W. Suppose we have an accumulation point W. And let's prove that actually we don't. Well, how do I prove that I don't have an accumulation point? Well, basically by proving that this W is not a limit point of other things. And so one way of proving that is by showing for you a little ball around W that doesn't contain anything else in W. Okay, that's what you do in topology, and that's what you do if you don't know topology and you want to think of some sensible way of doing this. So I'm going to find this for you. Okay. And the way that I'm going to do it is the following. Let's go back to this other picture of, do you remember the Tits cone? So remember the way this worked is, I'll draw for you the only picture that we were able to draw of a Tits cone. It looked like this, where basically the Tits cone was something that had one chamber per group element. Okay. So it had a main chamber called D, okay, and then reflection was just kind of like going to the, I mean, these faces were like generators. In this case, they were A and B, and for example, this was AD, this was BD, this was BAD, etc. We had one chamber per group element. Okay. Now I have a group element, which means I have a chamber. So I have some chamber over here which is called WD. And so let me define U to be the set of, again, we're thinking of this as living in R to the n squared, right? So let U be the matrices A, which, I mean, let's take some point here, X. Okay. Now we know that our group acts on X, and where does it send? Where does W send X? Well, the only thing that we know is that it sends it to this purple part. And so I'm going to consider all the matrices that send X to this purple part. Okay. So, of course, the one reason that I do this is because W is in U, because W sends X to the purple part. Now, what's the point? Well, the point is that I need a technical condition here, which is that this set is open. So what you need in topology And what open means is that if you're in your set and if you kind of move a tiny bit, you're not going to fall off the set. Okay? But I think you'll agree that if you have some linear transformation that sends this point x inside my purple thing, then if I change by epsilon my linear transformation, I'm not going to fall off of this purple set all of a sudden. And you can make this precise to say this is an open set. Okay. So what did I just produce for you? I produced for you a purple set which is open. W is in it. Now, what I would like to claim is that no other group elements are in it. Okay. So claim no other W prime is in U. How do I figure out if W prime is in U or not? Well, I have to figure out whether W prime sends X to my purple part or not. But W prime is a different group element, so it has its own chamber. Maybe it's down here, W prime D. And W prime sends X to this black chamber, not to this purple chamber. Okay. Here's W prime X. And therefore, W prime is not here. So the only point of W in U is little w. So what I produced is exactly what I wanted to produce. A little neighborhood around my point W, which only contains W and no other group elements. And that's what it means to be discrete. Okay? So my group is discrete. Why is that an issue? Well, the thing is that this thing is positive definite, which means that it's Euclidean. Okay? So W is generated by real reflections, and these are not any of these strange reflections anymore. Okay? They're real. Okay? Now, what that means is that this is actually a subgroup of not just of the invertible transformations, but of the orthogonal transformations. So what is this? Well, this is the n by n matrices with A inverse equals A transpose. The thing is that what does a real reflection do? Well, a real reflection fixes a hyperplane and sends one vector to its negative. So that means that you can choose a basis so that the matrix of that transformation is basically that it leaves everything alone except that it changes one thing to a negative sign. And that means that their matrices look like 1, 1, a negative 1, 1, 1, 1, like that. Okay? This is what real reflections look like, and that means that they satisfy this property that the inverse is the transpose. Okay? Which means that, and it's easy to see that this is a subgroup, which means that this W lives inside this orthogonal. This is called the orthogonal group. Okay. Now, the thing about this orthogonal group is that, I mean, here's the general linear group. It's infinite. The orthogonal group is also infinite, but it's smaller because it lives inside there. And it's actually much smaller. How much smaller? Well, the thing is, you can prove that this thing is closed and bounded. Okay. Why is it closed? Because basically it's defined by an algebraic equation. Okay. Why is it bounded? Because if you think about this, about what this means, it means that the columns of this matrix are orthonormal. And that means that they have length 1. So if this is closed and this is bounded, and you have W lives inside here, right? Well, W has no accumulation points, and it's living inside a closed and bounded set, and that means W must be finite, because you cannot fit infinitely many things in here and have no accumulation points. So this, if you know what this is compact. And because W lives in a compact set, with no accumulation points, it must be finite. So I don't know. If you knew topology, then you see we're really using some things crucially, and if you haven't seen this concept before, I hope this makes sense to you anyway. You have this set which is of a finite size. You cannot fit infinitely many things, and not get really crowded at one point. Okay. So that's my proof of that direction, and we'll prove the other direction next.
Going back to the office, you're going wait, what was the second one? Going back to my office. Federico, Cesar and I want to go to office hours today.
Okay. You know where I'll be?
Something that we can connect on Skype.
Yeah, but we'll do it. This thing from, we'll see. What's that? Oh, this thing from the internet down.